Hello everyone, welcome back to EC475 HFSS tutorial. Today we're gonna talk about microstrip array antennas. In the previous sessions, we saw the radiation characteristic of a single element antenna. We discussed about it and analyze it. Usually, as you know, the radiation pattern of a single element is relatively wide and each element provides a low directivity or gain. In many applications, it is necessary to design antennas with very directive characteristics, let's say very high gains, to meet the needs of long distance in communications. This only can be done by increasing the electrical size of the aperture or of the antenna. By enlarging the dimensions of a single element often result in the more directivity characteristics. But there is another way, another efficient way to design a high gain or high directive antenna without any increasing in the size of individual elements. It's forming the radiation element in an array antenna and in an electrical or geometrical configurations. So in most cases of the array antenna, the elements of an array are identical. So like in this tutorial, we see the microstrip antenna and then form these elements into the array to increase the gain and directivity of the antenna. And we saw that by changing the input phase or amplitude of each single element, we can configure the beam, and we have a beam string capability. And also nowadays, by using some digital beamforming in this array antenna, this antenna enables us to have a multi-beam array, which is the basic of the 5G technology, and it is good to know about it. There is 5 controls that can be used to shape the overall pattern of the array antenna. One of them is the geometrical configuration of the overall array. Let's say have a linear, circular, rectangular, spherical, whatever, or the relative displacement or the distance between the elements, and as I indicated, the excitation amplitude of the individual and the excitation phase of the individual elements, and the relative pattern of the individual elements. And these 5 elements, at least 5, they can control the shape of the overall pattern. And by changing these 5 elements, you can manufacture the beam. Okay. Let's go to the HFSS and see how to design an array antenna and see the effect of the array antenna. So here we want to design at 30 gigahertz 4 element array of the patch antenna and see and compare the result with the single element. So let's go to the HFSS and define the parameters that we want to have for single elements. This is my substrate. From 0 sub x 5 millimeter 5, from 0 to sub x sub y and at h sub y, which is equal to 10 mil. That's the 10 mil is 20 mil is 0.5 and 10 mils is about 0.254 millimeter. Okay, this is our substrate, and assign a material which is the permittivity of, let's say, 3, and dielectric loss tangent is 0, 0, 0.70. It's the dielectric loss tangent in the relative permittivity of 3. This is our dielectric material. Define it, and let's define a patch antenna on it. And we have the ground plane. Sorry, this is a GND, our ground, and this is our substrate. So copy it. Minus tick. Tick is about 0.028 millimeter. So this is our PC, and change the material to the PC. We have GND under our patch antenna, and let's say define a patch. So the dimension of patch, let's say minus xp minus yp and h sub xp is equal to, let's say I design in 2.62 millimeter for 300 gigs. Sorry, 30 gigs, and yp is equal to xp. We have xp here, yp here, and the thickness of the piece. So we have our PCs, assign material, PC, and we need to feed it. Again, let's draw a box. Let's define a patch. Okay, and see the feeding, a little feeding, because we wanted to see the impedance, and we wanted to, because see the effective impedance and see the accurate impedance, we need to a little bit draw a feeding network, and a feeding line which is defined minus f minus yp, let's say minus 0.2 millimeter, and h sub xf is equal to 0.2 millimeter, x size is xf, x size is equal to 0.4, and the thickness. Okay. Yeah, that's gonna be okay. We can unite them, and it's gonna be okay. Let's say in a y direction. Okay, also I create a sheet in a xz equal to this. Okay, it's feed. We name it feed, and also it's assign a PC to them, to our feed line, and let's copy feeding size, let's say 0. In a y direction, the x size will be xf, x size will be h sub, and we apply it. Yes, that's gonna be okay right now. So let's unite the feed and the patch. I'm going to just say the feed. Okay, it's no problem, and have excitation in this port. Assign excitation, LAN port, next. You're already familiar with this process, so and let's have a boundary radiation. So let's define it in minus x minus 5 millimeter. Let's say lambda over 2, and again minus sub y minus lambda over 2, and minus again over 2. So lambda is for 30 gigahertz, lambda is equal to about 10 millimeter, 1 centimeter. Yeah. So x plus lambda one y. Sorry. The z size, let's say, have a 1500. Okay, we can see the box. Transparent it to see it inside the box. Okay, everything gonna be okay. Okay, radiation boundary. And now let's see. Set sphere minus 180 and 5 degree. 5 degree. Yes, everything gonna be okay. Let's validate, and we need the analysis setup. So let's say 30 gigahertz. Number of pass 10, 2%, 3, 2, and save the field. Okay. Let's say 25 to 35. Okay, and let's analyze it. Everything gonna be okay. So we need to plot real and imaginary part. We need to plot the far field gain. Okay. Need to plot far field gain dB. Okay. Let y equal to 0, let's say. Setting radiation pattern. Oh, sorry. Should be minus 180. Okay, I analyze it again. Oh, yeah. And see the input impedance at about 30 gigahertz. We have the, let's say, 30 gigahertz. We have the real input impedance of about 300, which is very large, and if we need to match the 300 to the 50 ohm, we need carefully to design. We will more elaborate on in the next few minutes to how to design a matching network, and how to see one example of designing matching network. And as you can see in this 30 gigahertz, we have the radiation, maximum radiation, with the gain of about maximum gain of about 7 dB, which is the good for a single element. If we want to increase more radiation gain and directivity, we need to form the array of this patch element. And let's see the result, 3D result of this pattern at 30 gigahertz. And you see the very wide angle beam, with the gain of about 7 dB. So let's go to the 3D component. Let's hide the radiation box and copy all the material and the long port, yes, and copy along a line. Let's say here you can define the 0 0 0, the point vector, the start point vector, and then let's say have 5 millimeter, which is the lambda over 2. The distance, usually the distance between the array is lambda over 2 because it has the most radiation agreement of each element. In theory, you will see, and you can read in your reference book, that lambda over 2 give us the high gain and reduce the grating lobe and reduce the side lobe level, which is not the desired radiation in the pattern of the array. Let's say 5 millimeter, which is the lambda over 2. Okay, we have a 4 element here, and we have a 1 excitation. Let's have another. Okay, this is an assign sheet. Assign excitation to other, long port to other, port number 2. Let's define. Let's go to the port number 3. Assign excitation again. Let's define, and let's go to the port number 4. Assign excitation, go to the long port, port number 4, and define a new line. Okay, let's do it again. Okay. Now we have a 4-element array antenna, and we want to excite it, so go to the excitation, edit source, and turn on all the ports. And now we should define, let's say for x size we have a 4 sub x. Okay, you can see the box, that's gonna be okay. It's the radiation, okay, and everything is fine. Let's analyze it and see the change in the gain and the pattern of the antenna. Because we had a 4 element, it took a little bit more than 1 element. This is a single element, you can remember it. After finish the process, okay, you can see the narrow the beam, and by adding some elements by array it, and in some radiation element, the beam bandwidth is decreased, and we can shape the fan beam, which is, or pencil beam, which is a very narrow beam. And you can see the gain plot, which is about 12 dB. We have a 7 dB, so normally when we double the array, it's increased 3 dB, and when we double and double the array, twice double the array, it's gonna be 6 dB. But there is just calculation, but in the simulation it's about 5.2 dB increasing against, and it's gonna be okay for the simulation. And you can see by adding a more element in the x direction, we have more pencil beam, more narrow the beam, we narrow down the beam. And by adding the more element in the y size, we can also narrow the beam in the y size and shape the beamforming. And also, let's go to the edit source. Let's by defining the phase and changing the phase of each element, you can steer the beam in whatever direction you want. Let's say 1 to dt, and dt is, let's say, 0 degrees. So the third element, 2 and 3. Okay. And now going to the Optimetrics parametric sweep, add a dt to have a 0 to 36 degree, and set 10. And let's analyze the setup. Okay, let's go to the animate. Okay, let's go to the animate and create the animation setup. And okay, also here we can see the radiation pattern, which is, we can see, let's say, the gain plot 2, the scale of 1, and transparency of 0.4. Yes, and it should move on the, okay, at the center point, but at the center point of the antenna, and you can see 1 is okay, something, say 21. Okay, and now we can animate the beam. Go to the parametric sweep, and yes. Now you can see by changing the dt, and the radiation pattern is changed. And let's say in dt, let's say 50 or 30, we can fix the beam. And let's say the dt is equal to design parameter, and let's say equal to 40 degree. And then We disable the parametric sweep to fix the beam at the dt is equal to 40 degree. Analyze it again. So you can see the main beam is changed in a minus 50 degree, and there is also side loop changing, and there is some grading loop here, and we can change the beam string in minus about, let's say, minus 10 or minus 15 degree. By changing the phase to 40 degree, dt, this changing happen. Or also you can see again the changing of the pattern of the antenna by changing the dt and the phase of each element. You can see here you have two lobes. You have one main lobe. You are creating a three lobe here, two main lobe, and that's it. So let's move on to see how to design a feeding network of this array antenna. As you can see in this design, there is a 4 array antenna, patch antenna, and feeding by a 50 ohm coaxial cable, and we should notice that the line should be equal from the coaxial line to each antenna, because they need the same phase. And if you wanted to change the phase of each element, you need to put some phase shifter structure here, or have a delay line to have a specific phase shift for each element. By the way, how to match the input impedance of this patch antenna to 50 ohm? As you can see, the coaxial line is typically is a 50 ohm characteristic impedance, and so these two lines are parallel to each other, so it should be 100 ohm. And how to match the input impedance, as we saw in our design, it's about 300. How we can match the 300 to 100 ohm? So because in a manufacturing side, we cannot have it, because of the height of the substrate and the limitation of the fabrication. Let's say we cannot fabricate a line with width of less than 0.1 millimeter or something like that in a fabrication process. So there is some because of this some fabrication limitation, we should match this 300 to 100 in some tricks. And as you can see here, I developed some tricks here, and because we cannot have a 300 or macroscope line in such a substrate, so we use a 2 lambda over 4 transformer, as you can remember from the EM courses. The Lambda 4 transformer can transfer the input impedance to the desired impedance. So here I use the two Landover 4 transformer. One is here, so it's transformed the 300 ohm to about 30 ohm, and this 30 ohm again transform it to the 100. And by the way, by this transformation tricks, we can design a feeding network and match the input impedance of each antenna to the 50 ohm. You can check your reference about the Landover 4 transformers, and thank you for your attention. Have a good week.